fantastic to be here and look at this 2,000 developers using Cassandra. What an amazing sight. Over the last couple years, we've been working on these different versions of Cassandra. 2.1 took us an especially long time to get right. We had 7 release candidates, and the final release dropped this morning. So we're finally out. Thank you. I was a little bit worried. We released RC7 just a week ago. Had to make some last-minute fixes in there, but we're finally ready. What I'm going to talk about today is reality. So you can go download 2.1 now. You can try it out. Let me know how it goes. We've seen a lot of growth in companies using Cassandra, and we've put a lot of effort into making that process of learning the tool and being productive with it easier and easier. A critical piece of that was when we introduced the Cassandra query language, CQL, and started allowing people to leverage a little bit of that relational background that they had and bring that to Cassandra. And Cassandra was willing to meet you halfway, as it were. But part of that is that it's not just the server software that I work on, but bringing that power of the server to your application. And so we're also working on a DataStax drivers that present a uniform API within the constraints of the different languages that expose the full power of Apache Cassandra. So today, DataStax has 7 drivers in different stages of development. Now, if your favorite language isn't on this list, you're not out of luck. There are community drivers that you'll be able to use and take advantage of. But the DataStax drivers deliver the full power of Cassandra, and sometimes in some non-obvious ways. I've tried to diagram one of these in the upper left here, where the CQL protocol is an asynchronous protocol. So instead of having to send a request, wait for that response, send another request, wait, send, wait, I can parallelize that. I can send all my requests at once and get that reply back and lower my latency in delivering that data to my application by using this query pipelining. So all of DataStax's Cassandra drivers support this feature and other advanced features of Cassandra. So I've tried to illustrate that a little bit with these other 3 pieces of code here in different languages. You can see that across these languages we have some similar concepts. So I'm going to give the driver a contact point with the cluster. And with that contact point, it can pull in the replication strategy, the partitioner, the locations of the data centers, the machines in those data centers, and be able to use that information to route my queries appropriately. And I can specify a failover policy, I can specify a retry policy, and all of these are provided as a uniform substrate to the DataStax drivers. So one of the reasons that it's taken us a little bit of time to get these rolling has been that given Cassandra's distributed nature, building a driver is a little bit more involved than putting together a JDBC driver. Billy mentioned that one of the keys to Cassandra's success is its fully distributed nature. So I want to talk a little bit about that. I definitely agree that distributed nature, where each machine in the cluster has equal responsibility with the others, is really key to building a system that scales and that is sane to operate in the real world. The alternative, most other databases are built around a master-slave paradigm, where for each row of data, I have a master that's designated to be responsible for that, and then the master can replicate that row to 1 or more slaves. Master-slave databases make my daughter sad. And some of the reasons why are obvious, and some of them are a little bit more subtle. On the obvious side, when you have that master-slave design and the master goes down, then you need to have some kind of failover process. You need to initiate the failover, you need to elect a new master, you need to replay any necessary logs, and then you can finally start delivering results from that new master. Cassandra is less fragile than that because each replica is fully capable of serving your requests. There's no special process that we need to take to handle failure. Failure is a part of life, and it's a part of clusters as well. So if I have a request and I route it to this replica, and that replica goes down, I don't need to have a new master election. I can go and immediately retry that request to a different replica and pull that out to my application. So if you look at how this might look in a real cluster, you know, if I have to have that failover process, I have a period of downtime. You know, my application's unavailable. But with Cassandra's rapid read protection, there is a dip. I'm not going to sell you, cookies and rainbows here, but there isn't that period of downtime. I take that performance dip because I do need to retry those requests. I had a whole bunch of requests in flight. The machine they were routed to went down, so I had to retry those. So there is a performance impact. And that impact gets smaller as your cluster grows larger. Because in this case, it's just a 4-node cluster, so I lost a quarter of my capacity. I had to retry 25% of my requests, and you can see that reflected in the graph. Now, a little more subtle implication of having a fully distributed architecture is that it helps you not just when there's failures, but it helps during day-to-day operation, even when everything's humming along smoothly. This is a graph of a Cassandra cluster in England. And at the bottom, we have the median response latency, and that's hovering around 700 to 900 microseconds. And so that's pretty good, that's pretty fast, but other databases can deliver a fast average response latency. But what's unusual about Cassandra and about the distributed architecture is that because there isn't any master bottleneck, I can load balance those requests around all the replicas, and so even a temporary spike on a single node doesn't have to slow down everyone. So at the top here in blue, this is my 99th percentile latency. So my slowest 1% of requests are still completing in 1200 to 1500 microseconds. So that's what that power of that architecture can deliver for you. It's not just fast average speed, but consistently fast speed, even across failures and even across temporary load spikes. One final implication of this design is operational simplicity. So I think it's fair to say that Netflix is an unusually sophisticated Cassandra user. So I'm not going to get up here and tell you that you can all manage 2,500 nodes with 2 DBAs. But I will claim that having that distributed design where there's no special master nodes, there's no special lock managers, this simplifies operations dramatically, and it eliminates entire classes of problems that you'd have to deal with. So I think if you're looking at NoSQL as a whole, I think you can categorize systems in NoSQL in kind of 2 categories. The poster boy for one of those is MongoDB on the left, where it's all about dealing with schemaless data. Throw the data in, evolve rapidly, prototype that, and figure out what it all means later. On the right, I think Cassandra's the poster boy for dealing with problems of scale and availability. And while the features on the left are nice, and it's good to have a flexible schema and so forth, if you don't have the scale and ability, you're going to have a bad time. More seriously, though, when you're dealing with customers that have big problems and are willing to spend money to solve those problems, you're competing with Oracle. And that's who DataStax sees in competition at most of our customers. And people ask me, what are you going to do when Oracle wakes up and realizes that wishing Cassandra would go away isn't working? And my answer is that you can't duct tape a bicycle into space. If you need to exit the atmosphere, you need a spaceship. If you're building an application that needs scale and performance and availability, Oracle has more money than God. But they can't bolt those features onto their database. So I want to switch gears now. I want to talk about 3 categories of enhancements that we're delivering in the just released Cassandra 2.1. So I want to talk about performance, I want to talk about some operational improvements that we're making, and I want to talk about how we're delivering enhancements to the SQL data model to allow you to build your applications more effectively. So with performance, we've got some pretty big news. So at the top, I have the 2.1 SQL performance. The green line in the middle is actually 2.0 SQL performance. And then these lines at the bottom, the blue and the red, these are SQL and Thrift in 2.1 and 2.0 respectively. So I've been up here on stage last year, as well as at other conferences, telling people, just because we've added the new SQL API doesn't mean you need to rewrite your Thrift applications. So if you were an early Cassandra adopter, you build that application using Thrift, we're not going to take that away from you. We're not going to make you rewrite those applications. But, so I'm not going to beat you with a stick, but I do have a carrot. So if you're bumping into some, you're maxing out your cluster, you could throw hardware at it. That's a totally valid solution, and that's one of the things that Cassandra allows you to do. But alternatively, you can probably double your performance now with 2.1 by switching to CQL. And the potential has been there. We designed the language and the protocol to enable these optimizations, but it took us a little while to actually deliver them. So everything's a little harder in practice than it looks on paper, but we've delivered that in 2.1. Now, I want to look at, this is a best case scenario, right? This is 100% pure reads. There's no compaction going on, no messy writes hitting the commit log. So this is a best case scenario. Let's look at a kind of a worst case scenario. So this is what my operations per second looks like on a system where its data doesn't fit in the page cache. And so what I have on this blue line here is I finished a compaction, I ramped up my speed, I started another compaction. So this jagged area on the left, that's where it's compacting. So, if you remember the dark ages of 0.7 and 0.8, Cassandra, a compaction could seriously impact the performance of a Cassandra node. Then we introduced compaction throttling. So that works pretty well. So this performance line at the top, it's not a completely flat 100% uniform, but it's pretty good. We're delivering a lot of operations per second, and it's pretty consistent. But then this cliff here, this is when the compaction finishes. And the reason why it drops is that we've written out new data files, and now we said, okay, let's throw away the old ones that were in the page cache and we were serving the reads from, and we're going to direct those reads to the new file, and it's not in the page cache. So every read is going to be a seek on disk until we pull that into memory and it warms up, and then my performance ramps up rapidly once that happens. Here's what that looks like in 2.1. So, thank you. So what we're doing is we're actually incrementally pushing reads from the old data files to the new ones as that compaction's taking place. And so there's no big impact of all of a sudden we've switched from hot to cold. We're incrementally putting that in at a pace that the system can handle. And this happens automatically. If you might remember the old populate IO on page cache settings where you can try to guess at what a good value for this was for your cluster. that manual tuning's gone. This works automatically. I want to look at writes as well. So this is a similar graph to the first one we looked at, with 2.1 in CQL in orange, 2.0 in CQL in green. But this looks a little different. The performance is a lot less consistent. So we've got these miniature pauses where the performance drops in half temporarily. What's going on there is actually, this is a pretty beefy machine. This is a 32-core machine. And our commit log is limited to a single disk. So that's actually the bottleneck. So if you disable durable writes, then this actually smooths out. But disabling durable writes isn't a realistic solution for most people. So what we're working on for a 2.1 minor release is we're pursuing two approaches. One is to compress the commit log, which is going to reduce the volume that we're throwing at that commit log disk. And the other is to be able to parallelize the commit log across multiple disks. So for very high-end hardware, these are some improvements that we're looking to make. So on balance, though, Cassandra 2.1 looks very good against the competition. So this is a simple benchmark that I ran, single node, not trying to do anything fancy, looked at 3 different workload mixes. Definitely not trying to say that this is going to be representative of every workload out there, but I do think it's a fair assessment, and I think that you'll find similar things as you do your own investigations. So the code that I ran this with is my GitHub fork of the YCSB benchmark suite. So if you're paying attention to these things, the author of YCSB has moved on to other things, and the Yahoo branch is basically unmaintained. And so what I did is, you can look at the commits, but I haven't done anything nefarious. I've mostly fixed bugs, and I've standardized all these databases on all doing durable writes. So that removes one of the big discrepancies in performance is when subsystems are doing durable writes, other systems are not. So all of these are going to be doing durable writes out of the box. And then we've made some other improvements. For instance, we've added a CQL driver for Cassandra. Check it out. On the data modeling side, we've added a couple features here as well. A big one is doing some enhancements with lightweight transactions. So I introduced these to you, for those of you who were here last year. These were introduced in Cassandra 2.0. I talked about them at the summit. Just to summarize really briefly, a lightweight transaction means that I can specify a clause at the end of an insert or an update. And I can say, only apply this if some condition holds true. So I can avoid race conditions on inserting a new user by saying if not exists. So even if I have 2 users concurrently trying to grab that prestigious Patrick McFadden account, then only one of them is going to succeed. And the other one will get back a reply that says, it actually did exist, here's the row that exists, now do you want to modify that row, or do you want to try again with a different account? At that point, it's back to the application logic to figure out what to do when that transaction fails. But we've expanded this beyond just single statement transactions. So I want to give a couple examples of this, but first I want to introduce another new concept, which is static columns. And this was introduced in Cassandra 2.0.6. So midway through 2.0, we were able to get this in without destabilizing 2.0, and we didn't have to wait for 2.1 to deliver this. So what you're looking at here is I have kind of a transaction ledger or a bill ledger, and I have a static column here. I have a static balance column. And what that does is, just as in Java, and we're Java programmers who work on Cassandra, so we're not very creative. I mean that in the best sense of the word, right? But in Java, a static field of a class is one that's shared across all the instances of that class. In Cassandra, a static column is shared across all the rows in a partition. And so what I can do with this is I can atomically update my balance at the same time as I'm inserting a new bill. So what I'm going to do is I'm going to insert a new bill here for $200, and at the same time I'm going to reduce the balance by 200. In this case, this poor fellow's overdrawn. But what will happen is, if someone else has performed a transaction between the time that I read the balance and the time that I went to apply this new bill, then this entire batch will be rejected. So we've added lightweight transaction functionality to batches. Now, there is a limitation here, which is that all the rows in the transaction need to belong to the same partition. So that's still the unit at which lightweight transactions function. But you can now have an arbitrary number of inserts and updates mixed in to a batch that can be part of a single transaction. I'll give you one more example. This is from a real Cassandra customer. They had a requirement where they needed to build an event log where the log has producers of events and also consumers. And their business requirement was that after a given event was observed by a consumer, it's illegal to create new events with sequences older than the most recently observed one. So the way we can do this using lightweight transactions is we'll create an event log table, and we're going to have a static sequence number. And then we initialize each partition with a sequence number of 0. Once we've done that, we can insert a new sequence and increment the sequence number, insert a new event and increase the sequence number as part of a transaction. And so that's going to guarantee what we needed, that sequences never go backwards. Now, user-defined types, this is now new in 2.1. This is not in 2.0.6 anymore. User-defined types are new in 2.1, and they allow you to build hierarchies of data in your Cassandra rows. So you can think of this, if this helps, you can think of this as a type-safe document database. So what I'm going to do is I'm going to I need to create my types before I can use them. So in the upper left here, I'm creating an address type. I have 3 primitive fields, and I have a collection of phone numbers in each address. Then in my create table, I have a map of addresses. So I have text keys, and I have address values. Now there's a keyword here that you haven't seen before, which is frozen. And so what this says is, this is a bit of forwards compatibility. In 2.1, user-defined types are stored internally as a blob. And so what that means is, I can't take an address and modify just the street. I need to replace that entire address struct with a new one that has the modifications I wanted. And so we have the frozen keyword to give you that connotation of this type is a single unit. It's been frozen together, so you can't destructure it at a per field level. In 3.0, we're going to introduce mutability to user-defined types, and so you would use that just by omitting the frozen keyword. In 2.1, it's required. So once I have that type created, that table created, I insert some data, I can pull out fields from that without having to pull the whole address type. So the frozenness only really applies to updates. I can still pull out individual pieces of that in my select, as I've illustrated here. Another new feature in 2.1 is collection indexing. So we've had indexes on primitive fields for years. We're adding that to collections now. So here I'm creating a table that has a set of tags associated with each song. And I can create an index now on those tags and then say, give me songs whose tags contain blues. And then I get those back. So again, this is the same index design as the existing Cassandra indexes. So it's primarily meant as a convenience because we are having to do a scatter-gather query across the cluster to pull in the results from the different nodes. But it can be very useful for low-volume types of queries. The last category I wanted to talk about for 2.1 is operations and improvements we've made for operations. So counters has been a bit of a messy place for Cassandra users. And the core of that messiness is how the counters were implemented under the hood. And specifically, when you tell Cassandra 2.0 to increment a counter, it writes that increment to the commit log. It doesn't write the full counter value, it just writes the increment, and then it applies that increment asynchronously. So that gives me really good insert performance, but it has some interesting implications. So just to visualize that a little bit, here's a fresh counter. I've done its first increment. So my total value of the counter is 1, and the increment that I wrote to the commit log is also 1. So far, so good. The next increment I have, I also add to the commit log as the increment value. So now I have 2 entries of 1 in the commit log, but the total counter value is 2. My third increment is actually reducing the value by 2. So now I have a -2 in the commit log. My total counter value is 0. So again, this allows me for maximum insert performance, but it has some hairy implications for when things go wrong. So normally, if I lose power, I'll replay the commit log, and I've got my data back, no problem. But there's a narrow window for 2.0 counters where if I lose power, immediately after flushing this counter value of 3 to disk, or counter value of 0 to disk, but before I tell the commit log that I've flushed it, I'll replay those counts again the next time I start. So I have the counts applied on disk, but I'll replay them again because I lost power during that narrow window. So I've double counted some of my data. So to fix this, we've replaced the engine while it's running. We've switched counter designs while maintaining compatibility with 2.0. And, I'm sorry. I didn't update the slide title. So says 2.0. This is actually 2.1 now that we're looking at. That's what threw me off. So I'm writing now to the commit log the total counter values. So now when I go to replay, it's 100% replay safe. It's idempotent just like every other update in Cassandra. So the hard part of this was actually not making this change, which we've known how to do for a while. The hard part was making this change while maintaining compatibility across an upgrade. So while you're pulling out 2.0 machines, or you're killing the 2.0 process, replacing it with the 2.1 process, so you have a mixed cluster of some are 2.0, some are 2.1, some are thinking in terms of deltas, some are thinking in terms of full counter values. That was the tricky part. But we were able to pull that off and make that upgrade happen without downtime. So what that looks like on the performance side is for low contention counters, which is how we recommend using them, is spreading out your counter increments across a number of different partitions. The peak performance is pretty similar for 2.0 in blue and 2.1 in orange. But the consistency of the performance is significantly better in 2.1. And that's because since we're not throwing all the increments at it and then merging those together asynchronously, we're generating a lot less garbage on the counter update path. That's basically why that's improved so dramatically. Now, if you look at high contention, where a lot of the counter writes are coming to the same partitions, then you'd probably expect the new design to work less well, because we had to add a lock internally to manage the concurrency of those counter updates, because I need to fetch the existing value and then store that updated value to the commit log. But we were actually able to add what we call a counters cache to keep the hottest counter values as basically raw Java atomic integers. And so with incrementing those is extremely fast, and we don't actually need to go the heavyweight lock path. So 2.1 in orange here, we were able to deliver about a 50% performance improvement over 2.0. So you'll note, if you were paying attention to the legend on the previous slide, we were pushing 40,000 updates per second. Now we're pushing 7,000. So it's better than 2.0, still not nearly as good as having low contention. Low contention is still the way to go. But if your business requires you to design a high contention scenario, then this mitigates that impact a lot more over 2.0. Besides counters, next to counters, I think the biggest pain point for Cassandra clusters has been repair. And so just to go over how that works briefly, when we repair across different replicas, each replica is going to go and build a hash tree representing the data in the table being repaired. And so at the bottom here in these rectangles, these are representing blocks of data from the SS tables on disk. And then we turn those blocks of data into a hash fingerprint. So that's what these circles represent. And then we can combine the fingerprints of different blocks into a parent hash, and so forth until we have a tree with a single root fingerprint of all the data in the table. So then we transfer these trees to the different replicas so they can compare nodes. And then they compare the root node of the tree. If those hashes are equal, then we're good. Nothing needs to be repaired. If they're not equal, we can drill into the left half of the tree. We can drill into the right, see where that discrepancy is coming from. And so every step, we cut the number of cells that we're looking at in half until we find the block or blocks in question that are making those hashes not match. Then we can transfer just that data over the network. So this design is actually very good at reducing the traffic on your network. It's very efficient at that. What it's not efficient at is the building process, the process to build that tree. I need to scan that entire data set every time I repair. So if I add more data to my system, I'm scanning more data to do the repair. And it's a linear operation. So if I double my data set, my repair takes twice as long. So what we've done in 2.1 is we've introduced incremental repair. I'll only need to repair the data that's new that hasn't been repaired yet. So that takes repair from being linear in the amount of data I have to linear in the amount of new data I have. So if you're ingesting data at a constant rate, your repair time will also be constant no matter how much data you have. Now to do this, we have to track which SS tables are repaired and keep them separate from SS tables that haven't been repaired. And as a consequence of that, we wanted to make sure that we didn't do anything unexpected when you upgrade. And so this new incremental repair is disabled by default when you upgrade. If it were on by default, Cassandra would look at all these 2.0 SS tables you had and say, oh, none of these are repaired. Now if I repair 10% of my token range, now I have 10% of my SS tables that are repaired. All you unrepaired SS tables, you're going back to level 0 to get re-leveled. And so that's going to inflict a huge amount of recompaction overhead on your cluster, and we didn't want to do that. So the way to avoid that is, when you upgrade, first you need to bring your SS tables up to the 2.1 format. And this will happen organically as updates happen and as compaction happens. But when you need to make sure that everyone's ready and everyone's been upgraded, then you can issue this node tool command to do that. Once you've done that, then you can run a repair and this first repair is doing an old style repair. It's repairing everything. It's not just trying to repair new data. And once you've done that old style repair, then you can use a tool called SS Table Repaired Set to mark those SS tables with the incremental repair metadata that says these have participated in a repair, and I don't need to repair them the next time. And once I've done that, then I can start introducing the incremental repairs with the -inc flag, and then you're good to go. One final kind of pain point that we addressed was the much-hated row cache. And so the best practice has been, don't use row cache unless you know what you're doing, but really don't use row cache. Because unless you have extremely uniform partition sizes, the old row cache worked in terms of caching entire partitions. So if I read a row from a 100 megabyte partition, it would pull that entire 100 megabytes into the cache. And even though we've introduced an off-heap option for the row cache, it still needs to get pulled back onto the heap to read results from that. So you have this 100 megabyte serialized blob of data getting pulled onto the heap to answer cached queries. It's not a good use of either CPU or memory. So what we've done for 2.1 is actually very simple. We've added this thing at the bottom here, this directive of rows per partition to cache. And so that's going to operate on the head of the partition, or the beginning of the partition. So recall that partitions are ordered by the collation columns. So I've got that in bold here. My primary key is target user, notification ID. Target user is my partition key. Notification ID is my collation element. So I'm going to tell it to order by those notification IDs in descending order. Notification ID is a time UUID, so I'm basically I'm caching the most recent activity in chronological order. So if I look at a couple partitions of data in this notifications table, I've got 5 rows in the Nick partition. I've got 1 row in the Mike partition. Mike doesn't have as many friends. But I've told it to cache 3 of these rows from each partition, so I'm going to cache the most recent ones for Nick and the most recent ones for Mike. And so that protects me from that pathological behavior of I had a larger partition than I expected, and now it's doing bad things to my heap. Finally, I do want to mention something about our testing and QA in 2.1. So when I talk about testing and QA and beta quality, of course the first thing that comes to mind is Windows. But we've actually put a lot of effort into making Windows a good platform to run Cassandra on for 2.1. So I'm not going to say that it's production ready yet, but I am going to say that our QA team has dug into it, and the obvious problems are gone. So I'm thinking of Cassandra 2.1 and 2.1.1 and so forth as kind of an extended beta for Windows. We're targeting 3.0 as the time where we can say, Windows is a first-class citizen, go and deploy on Windows with no fear in your hearts. So if you're thinking that might be something interesting for you to do down the road, I'd like to throw up the bat signal here and ask for help testing that, starting with 2.1. Speaking of the testing that the DataStax has done, this is the DataStax QA team for Cassandra. So we have separate teams that work on our DataStax Enterprise and Ops Center and so forth. These people are dedicated 100% towards working on open source Cassandra. And a year ago, only one of these people worked at DataStax. So this has been a big impact on our 2.1 release process, and that's why we had 7 release candidates, and we're able to deliver a much more stable Cassandra 2.1. So with their help and your help in the community, 2.1 is our best release yet. And I look forward to seeing how that can help you in your business. And with that, I'd like to bring Billy back up to the stage to tell us about our sponsors and about where we're going from here for the rest of the conference.